Hello everyone again. Today I will present about detection and characterization of habitable exomoons. Basically, I will talk about exomoons and in the JWST data. Basically, it is a very broad field, and I will basically talk about the original works we have done, and I will try to link on the few other things that can be done in near future. First talking about exomoons. We know there are several moons in our solar system, more than 150, and out of there are quite a few big moons in our solar system. But if we talk about planetary system outside our solar system, we actually don't find any moon discovered till now. There are a few candidates, but we don't have any confirmed exomoon candidate, any candidate that have been confirmed till now. Basically, what is stopping us from discovering an exomoon? The first thing is the orbital radius of the discovered planetary system till now. So if we talk about the main detection techniques of exoplanets, there is two techniques. One is transit method, one is radial velocity method. Now, as we know, the transit method detection probability is actually biased towards discovering close in orbit exoplanets. So if you see this case here, it is a system Kepler-69, and here there is a planet Kepler-69b. It's in a very close orbit compared to this is a typical solar system. This is a Mercury orbit, and here, so you can see here the planet is in a very close orbit. But fortunately, in this case, there is another planet discovered in a wider orbit. But for most of the cases of our discovered planetary system, exoplanetary systems, we only have found most of the planets in a very close in orbit. Now, what is the problem with having a planet in a closing orbit? So, from the evolution of planetary system, that theory we have till now, these planets which are found in a very close orbit can't be found there. They have to migrate from a wider orbit. And suppose during the formation period, if there is a moon present around such a planet, it can't exist when it migrates to an inner orbit. It's because of tidal force affected on the moon. So there is a concept called Hill radius. So it depends on the radius of the orbit of the moon. And if the planet falls within a certain Hill radius, actually the moon will be lost from the planet. So that is the reason why we have, like, out of 5,000, more than 5,000 exoplanets, most of them are in a very close in orbit and they can't have an exomoon. That is the first limitation. So that is actually reducing the domain for finding an exomoon nowadays. And this is a rare case where we have a planet in a wider orbit. So there are a few exoplanets discovered till now, and more will be discovered in a next few years, because there is this test survey is going on now, and this is from Kepler survey as well. You can see. So to discover a planet in a wider orbit, first of all, the probability is very less for it to be transiting. The second is it will transit in a longer time period. So suppose there is a planet like Earth that will transit once in a year, and we have to be detecting of having the survey for over a year to actually find it. So the probability is decreasing this way. So this limitation is actually going to be solved as we move forward, and there's going to be our TESS mission, which is going to discover more than 10,000 planets, and many other modern missions are coming, like Plato in future. So this is about the second problem I will tell you now. The problem is the moons are very small. So here you can see this is our typical sun. Here is Jupiter, and Jupiter is very small. Around radius is 1/10, and then our Earth is again very small compared to Jupiter. It is around 1/10 of the Jupiter. Now our mass, our moon, moon Luna, is again extremely small compared to the sun. So for a exoplanetary system, what happens? How we discover it? That if this planet comes in front of the star, it actually offers some of the light coming from the star. Now, if a planet like Earth comes in front of the star, it will occur very less light. It is actually very difficult to detect a planet like Earth itself. Kepler mission has discovered a few Earth-sized candidates, and just imagine if a body like Moon that is very small, if it comes in front of the star, it will be like it is actually there. See, it is Jupiter. There is the Earth is there, and there is Luna. You can't even see it in this picture itself. So that's how much light it occurred. It will occur. It will be very less, and we can't see it with the existing instruments. So what is going to change over there? Where we're having JWST recently commissioned, and there are other missions like TMT, ELT. They are extremely big telescopes, and there is going to be also missions like Plato, which can. And there is also another mission called KIOS from Europe. So these missions actually going to have much more precision photometric capability. So that is how we are going to be capable of detecting exomoon candidates in future. Now, if we suppose we from any of this survey, suppose from JWST, the survey, suppose we come across a exomoon candidate. Suppose from the light curve we can see there is a signal somehow, but we have to actually model it to characterize it, to confirm if it is a exomoon or not, and to know exactly what is the dynamics, what is the size of it. We actually need a model to model the transit of an exomoon. So now we know there is a model to model the exoplanet transits that is quite well known, and the most accepted model is by Mendel and Nagel from 2002. Now, for the part of exomoons, there haven't been much of study in this field because we are basically limited by resources in this field till now. But there is one or two models from previously, but those models we don't know, like they are very complex and they are not very capable. Like we don't know if they can be easily implemented on observational results. So here we have worked on finding an analytical light curve model for exomoon transits. So I will talk about the problems, the limitations, what we have to define this model. Then I'll tell we have overcome these limitations or problems. The first problem is it is a 3-body system now. It is no longer a 2-body system. A 3-body system, we can't directly solve the orbital dynamics. Okay, so what we can do, what we have done is we have considered the planet and the moon to be a 2-body system. Okay, now for this 2-body system, there is a barycenter here, and we consider the barycenter follow a similar orbit around the star that the planet would have followed in the case of there is no moon present. So basically, the barycenter is following a Keplerian path around the star. Now this solves our 3-body problem. Now what we can do, we can just like modeling the exoplanet transit, we can just see this barycenter moving around the star. Now this planet and moon both will be orbiting around this barycenter of the planet-moon system as well. Now the first step would be to find the distance in the sense of the sky projected distance that we can call as a separation between these 3 bodies to actually track their orbital properties. So for that, what we can do, for the case of a single planet system, it can just transit in front of the star at a particular impact factor called B. So how much distance it is transiting from the center of the star. But in the case of for the case of planet, actually this orbit is, this inclination of that orbit is the inclination angle. That is how much the orbit is inclined with respect to the sky projected plane. But the what do you call this thing, like which direction this orbit is inclined towards, like this or like that, won't affect. Like, but when there are 2 orbits, actually there is a factor. So we have to understand every time what is the difference in inclination of these 2 orbits. So for that, another parameter is this alpha and beta. So it is like M says moon B is barycenter. So basically we have 2 orbits, and for 2 orbits we have 2 inclination angle, and there is another angle which is defining the angular separation between these 2 orbits, side-pointed orbits and major axis. So that is how we solved this problem of solving the separation between all these 3 bodies. Now there are 22 cases of alignments. Now, as I was telling you, we have solved the distance between these 3 bodies. But for different alignments of these 3 bodies, we have different cases for which we have to solve to find how much light, how much flux we are getting from the star. So basically, all the possible alignments that we can actually put into these 22 cases that I put here. And if you can see, the first few cases are very simple. This blue is the star and red is the planet, green is the moon here. And like first few cases are very simple. And if we are going forward, like after 11, 12, 13, 14, this still it is very simple case. Why I am calling it simple is, you can see the occulting area between these two bodies, any two bodies here or here. It is like a radially symmetric area. Okay, here it is a radially symmetric area from the star center. Here also it is a radially symmetric area from the star center. So for a occultation like this, actually we have an analytical formalism to find how much flux we are getting using Mendel and Eagle's formulation that uses a quadratic limb darkening formula for limb darkening effect. But for a more complex system of three bodies, actually we have areas which are not now radially symmetric. From 15 to 22, case number 22, we don't have we have areas that are not radially symmetric, so we can't use that analytical formalism. So what we can do is, we can consider small body approximation. That is what I will tell you. So suppose this is the area of the interaction of three bodies, and we can't directly find how much flux this area is occulting from analytical formula. But what we can do is, we can consider whatever flux is occulting between this radius is considered to be uniform over this annular radius. So from that, what we can know is, like because this area has to be very small, because this moon is not that big, so that will be very good approximation. For more information of small body approximation, you can see Mendel-Eagle 2002. So that solves this problem of finding 22 cases. Now, for this 22 cases, I have shown here the conditions at which these cases is. Okay. So I have shown the cases at which these conditions will satisfy. Actually, first few cases are very simple. We can find them just from the difference between the separation between these two bodies. But for the last few cases, actually we have introduced another factor here. That is the distance from one body center to the intersection point of the two bodies, that we have used in the last few cases. That is a unique approach from our side, and these actually solved these cases to be conditions to be very simple. And these are actually this side AOP and AOM are the occulted area by the star, by the planet and the moon by the star. So actually, and then another problem was the finding the idea of coalition of all three bodies. Actually, this can't be solved analytically, but there is a approach by Howell et al. 2006 that we have adopted. If we know the coordinate of center of these three bodies, we can actually find the area of occultation. Actually, I'm not going to show the mathematical formulas here. That will take a lot of time. And basically, I will show you some of the light curves we have obtained from our this formalism. Basically, it is a system with Jupiter-like planet, and we have kept the moon to be Earth-like in size, so that you can see there is this is a transit signature of the planet, and this is transit signature of the moon. And we have kept this system in such a way that where this transit signature of the moon will follow after the transit signature of the planet. And similarly, these we have taken an Earth moon type of system around the M star, so that we can also see the moon's signature is here. And what this red curve and blue curve signifies here is a transit time variation effect. So if there is no moon present, the red light curve will be the what it will follow. But if the moon is present, the planet is getting displaced because of the gravitational impact. So that is actually shifting the planet's position. So this is also is a useful tool to find new exomoons. Okay, so that's what I am going to talk about. All this is the last slide actually. So basically, using this formula, and we have the light curve, and there is a lot of opportunity in the JWST and other large missions era. So actually, we have also calculated the if we can find any exomoon with JWST. So we have found that for a star like our sun, we can go up to a size of Ganymede and Titan to find an exomoon. If the star is a lower mass star like K2 type star, K type star, then we can go up to size of our own moon, Luna, or Europa size of sun. So yeah, that is all in a brief about this type of this field of work, and there are a lot of others that I can discuss. If you are interested, you can approach me. So thank you very much. Couple of quick questions. Yes, Akira.
How many
So this one we have consider for this limit I told you, no, the size. For this sizes we have considered only one transit, and but we have to beam it for a 2 hour or 3 hour photometric beaming. Then we can detect it from one transit only. If we combine 1 hour transit, we can even go to a smaller size of moon. Yes, Soumya.
Nice talk. I have a very question that some planet has more than one exomoon. How the geometry is used?
If we consider only a planet and moon system, and if we consider the moon where mass to be very less, so then we can actually consider each moon to have its own geometry around the planet. So suppose for a giant planet like Jupiter, and the moon is very small like Titan or Ganymede, anything, the actual how much impact the moon is putting on the planet will be very small. Because I was showing the Earth moon system, the TTV was significant.
I'm telling more than one.
Yeah, that is what I'm telling. So the TTV is how much impact a moon is putting on the planet. Okay, if we go for a giant planet, actually we can put individual planet light curve and combine it. But if the planet is small, like Earth moon system, we have to consider interaction between the two moons impact on the planet. That we have not worked till now, but that can be put into. We have to go into more robust formalism to implement that more number of moons.
Long live India and France friendship.